Hello everyone. Before we get started, let's clarify a few key points. In today's video, we adopt the definition of including zero in the set of natural numbers n, and n plus is then denoted as the natural numbers excluding zero. We will also be discussing open sets from the standard topology on R, which are simply those open intervals that you are most familiar with. So no worries if you haven't learned topology. Feel free to pause the video for more details. As you know, the intersection of any collection of closed sets is still a closed set, and the union of any collection of open sets is still an open set. But what about the intersection of open sets, or the union of closed sets? Today, we will explore two set equalities. We will prove the first one in this video and prove the second one in another. The first shows that the intersection of a countably infinite number of open sets can be a closed set. The second exemplifies that the union of a countably infinite number of closed sets can be an open set. These examples are interesting and elegant. That's why I choose to prove them in today's video. Know that there are two common tricks to prove set equalities A equals to B. The first method is we split the problem into two parts by first proving that A is a subset of B, and then vice versa. The second method is, based on the set description, we try to prove a sequence of equations. Mostly, we just prove that A equals to C and C equals to B, thus A equals to B. Today, we will apply the first method. But how to prove each part anyway? Simply take any element from the set A and prove that it's also an element of the other set B. This proves the inclusion, which infers that A is a subset of B, and the inverse can be proven in a similar fashion. Together with these two parts, we have shown that A equals to B. Okay, let's turn to our goal today. Take a look at the first equation shown here. As discussed, we split the proof into two parts. Let's proceed to solve the first part. We will first apply the first method exactly the way how I described it. Then we will find out that by simplifying the proof, it could be much clearer and more compact. That's why I mark this the informal proof. Given any x in the closed interval AB, it's clear that this interval AB is contained in the open interval A minus 1 over n, B plus 1 over n, for any natural number n greater than 0. Thus, we get this inequality, which seems to be quite obvious. It turns out, x is definitely an element in this open interval as well. Since the x that we chose is random, we know that AB is a subset of this open interval, which is exactly what we mentioned from the beginning. So we find out that it's too verbose to simply copy the pattern of the first method. But anyway, the logic was still valid. We can then move on to the formal proof. Essentially, we only have to show that for any given n, these inequalities that we have discussed hold true. This immediately shows that the closed interval AB is contained in this open interval. We only have to get to know the relationship between this open interval and the intersection of all the open intervals A minus 1 over n, B plus 1 over n, n equals to 1, 2, and so on. It's then easy to realize that this chain of inclusions always hold true for any given n. This implies that the intersection of all these kind of open intervals, k from 1 to any given n, equals to the open interval A minus 1 over n, B plus 1 over n. Voila, this proves that the interval AB is indeed a subset of the intersection of these open sets. Let's move on to the second part. Given any x in the intersection of these open sets, know that we can obviously regard this as for all x in the set anyway. We get this inequality immediately for any n. By removing a and b to the other side of the inequalities, we obtain these two inequalities. We then want to show that x is also an element of the closed interval AB. In other words, a is less or equal to x, which in turn is less or equal to b. Since it's not obvious whether it holds true or not, we will use proof by contradiction here. First, in order to prove that a is less or equal to x, we assume that a is greater than x, and this inequality holds true immediately for any n. A common idea is to then take this n to infinity and see what happens. Just as what we expected, this inequality couldn't be true, which leads to a contradiction. So we have proof that A is less or equal to X. The proof of B is greater or equal to X is similar. I will leave it to you to try. So we have proof that X is an element from the closed interval, which shows that the intersection of open intervals is a subset of the closed interval AB. With these two parts of proofs, we have shown that this set equality holds true. That's all for today. In the next video, we will apply the well-known Archimedean property to prove one direction of inclusion in this second equality. Before this, we will also prove the Archimedean property first. See you then.